All right, so we're going to look at some examples of using integration tables in order to complete some example integrals. And so I've put up a couple here, and we're going to just go through them. I have a table of integrals that I'm going to use. The one that you use from your textbook or that you may have found online may not include literally everything that is in this table. Tables tend to have very common things that overlap significantly, but then there's usually a few differences between them. So if you can't find the specific integral that I'm looking at, it may be because it's just not in your textbook. And that's fine, because if you're looking at the table from a particular textbook, if you're picking problems out of the textbook, the problems for the table will correspond to the problems that are in its own table. So again, this is more sort of for the process. So in our first example, we have this function that is a combinations of sine and cosine. And so what we're going to do is we're going to go to our integral table. And we're going to see if we can find something that looks like this. So let's go to my table. So here's my table. Now, the most integral tables, they start out with the basic rules, and then they're broken up by category, by type of function. So we're going to go down to the sine and cosine portion of the table and see if we can find something that looks like what we have. So here's our powers of sines and powers of cosines and products of sines and cosines. And here is some rational type expressions that involve sines and cosines in the denominator. None of these look quite like what we have. And now we're down to tangents. So none of the examples in our table appear to look like the function that we have. So let's go back to our problem. And so what we're going to do then is we're going to try to do a substitution. If we do a substitution, then that may give us a different formula or different section of the table that we can look at. So since I have sines in my denominator and cosine in my numerator, I am going to make a substitution for u equals sine x. And then du is going to be equal to cosine x dx. And when I do that, my integral will become 1 over u squared plus 2u du. All right, so now that I have that, now what I'm going to do is I'm going to go to a different part of my table, and I'm going to look for a rational expression that maybe looks something like this. So let's go back to our table. And the rational expressions are further closer to the top. Let's go back to the very beginning. Here's our rational polynomial functions. So that's linear, so that's not what we want. Those are factors that are squared. That's not what we want. We have a u and a u squared, so that's not quite it either. We could treat this like a factor. So we could have something like this, perhaps. We could factor our denominator into u times u plus 2. That is an option. That looks like a fairly compact formula, so that one might actually work for us. Another option would be to use something like this, but then we have to check some conditions. Yeah, so I think this one that we were just looking at right here is we have a 1 in the numerator. We can factor the denominator. This is probably the one that we want. So what I'm going to do to make my life a little easier is I'm going to print screen. for this one formula, this was the one that we were going to use right here. And then we're going to back to our file. And so I'm going to actually just paste this right here so that I can copy it. Flipping back and forth between the formula and the sheet that you're working on can sometimes be weird. So I'm going to rewrite this integral in the factored form that we need. U plus 2 du. Oops. There we go. So what we need to identify in order to apply the formula is we need to identify all the coefficients. So if I'm going to let this u be my ax plus b, then a is going to be 1, and b is going to be 0, and c is going to be 1, and d is going to be 2. So this is my u factor, this is my u plus 2 factor. And so what that's going to do is that's going to mean that I can then apply this expression for my answer. And so this integral is going to be equal to 1 over AD is 2 minus BC is 0 because B is 0, log of U is my AX plus B divided by CX plus D is U plus 2 plus C. And so again, I can simplify this to just 1/2. And essentially this is a problem that you would solve by integration, by partial fractions, right? But now they've already done that for us based on these general coefficients. And so we have we've been able to apply our rule, but we're not done yet because we originally started with X, not U. And so we have to put everything back. This would be log of sine X divided by sine X plus 2 plus C. And so now we're done. Sometimes the trickiest thing about applying integration by tables is not trying to force your integral into a formula that doesn't really fit, but identifying what kind of substitution that you need to do in order to get a rule that does in fact work. Now, sometimes all you'll really have to do is apply an appropriate formula. So let's make some space for this one. So in this case, we already have basically just a rational formula. And so all we need to do is identify a formula that will give us X over a linear factor, and then identify our A, B, and C since we have different coefficients here. So let's go back to the table. And we're basically more or less in the right place. We need linear factors like these, but we need an X in the numerator. So we need this one basically. So again, I'm going to grab a screenshot. And then we're going to go back to our problem. And for this one, basically the only thing I need to do is I need to pull the 3 out of my integral. X over 2x plus 7. And then I need to identify that for my formula, A is equal to 2 and B is equal to 7. And I have my 3 on the outside, which I can't forget. So now on the inside of my parentheses, I'm going to apply my formula. I've got x over a, so x over 2 minus b, which is 7, over a squared, which is 4, and then log of ax plus b is 2x plus 7. And then the plus c can go on the outside. And this one I didn't have to do a substitution for. All I had to do was pull out my 3 and then find the rule that I needed to apply. So we've got another one that uses a different part of the table. So let's look for this one. So this one is going to be in the radical section, and we're going to need a sum of squares in the denominator. So we go back to our table. Let's see, the radical section is after this one, radical functions. We need not a linear radical, we need a sum of squares radical, and we need it in the denominator. So here's our sum of difference of squares, but we need it in the denominator. So here's that, but we have an x up top. Let me double check my formula. Oops, it's 3x over x squared plus 8. So we can use this one. Yes, this one looks like the appropriate one to use right here. This one we could probably do by use substitution if we really wanted, but we're going to use the table since that's what we're here for. So again, I'm going to take a screenshot of my x over my radical. And we're going to go back to our problem. And this is our formula. Again, we're going to pull out the 3. And have x over the square root of x squared plus 8. And so our a, so the tricky thing about this one is that our a is going to be the square root of 8, or 2 radical 2. Because again, this formula, this is x squared plus a squared, and we have x squared plus 8. So a is the square root of 8. And so now if we apply our formula, we're going to get 3 times a bracket, and we're going to apply our formula. And this is a pretty straightforward one. Again, we could have done this by substitution. We're going to end up with x squared plus 8, all under the radical, plus c. And we don't end up getting an extra half or a 2 or anything like that, because the square root will give you a half when you take the derivative. And then when you take the derivative of the x squared, you get a 2x, and the 2 and the half will cancel. And same thing in the reverse order. So you end up with just this 3 as our main coefficient. So you can, in theory, use these tables for very simple things, but certainly they're more useful when things become much more complicated. Now let's think about our e to the x, our cosine e to the x problem. Again, if we go back to our table, we might think, okay, well, let's look in the exponential section, logarithmic functions. These are our exponential functions at the end. Do we have any examples with our cosine? And we don't. And so therefore, again, we're going to try to do a substitution. So the substitution that we would most likely want to do here would be u equals e to the x, and then du is equal to also e to the x dx. And that is going to rewrite our integral as just arc cosine of u. Now, if we were to do this by hand, we would need integration by parts. That's how we would proceed for this problem. But now we're going to look at a different part of our table for an arc cosine or an inverse cosine rule. So not in the exponential section, not in the log section, not in the hyperbolic trig section. We're looking in the inverse trig function section. There's arc sine. Here's arc cosine. So again, I'm going to take a print screen. And we're going to go back to our other page. And so we're going to apply this rule, and we're going to end up with u arc cosine u minus the square root of 1 minus u squared plus c. But again, we didn't start out with u's, we started out with x's, so we have to put all of those x's back. E to the x arc cosine e to the x minus the square root of 1 minus e to the 2x, because that's e to the x squared, plus c. All right, so I got a couple more. Let's look at we've got another radical here, but we've got a power outside of our square root, and the square root is not in the denominator. So let's go back to our table. We're going back to the radical section. Radicals. We don't have radicals in the denominator here. We have them in the numerator. And we have a product. Now we have a cube and not a square. So let's see if we can find an appropriate formula. So we've got something with a linear generic formula, but we don't have a linear expression. We have a square, sum of squares under our radical. So we would need something like this, except multiplied by x cubed. Here's this multiplied by x. Here's this thing multiplied by x squared. That's a difference. We don't have a difference. So in this particular example, it does not look like we have a formula of the type that we need in order to apply it. Now we might be able to apply one of these identities, particularly this one maybe. We would have to do a substitution because we don't have x squared. I believe we have 2x squared. So that is a possibility. Another possibility that we could use would be to do a change of variable and then see if that produces a different type of expression. So again, the integration by tables is not necessarily going to save you all of the work because you have to match a formula that's available to you. And so if you have an expression as we have here that doesn't really quite match one of the formulas, then this is what you have to do. But we could try to apply this one. This one might actually work without having to do a change of variables because n would be 3. And then with a simple substitution to adjust our coefficients, we might be able to apply this one. So let's try that. Let's take our print screen and let's see if I can get all of the exponents and everything. All right, now we go back. All right, so let's think about this. So let's say I said u was going to be the square root of 2x. That way, u squared is going to be 2x squared. And just to be clear, I'll actually write it out. In that scenario, then I'm going to have du is going to be the square root of 2 dx, which means dx is du over the square root of 2. And that also means that x cubed is going to be, let's see, it's going to be x is going to be u over the square root of 2. So x cubed is going to be u cubed over 2, square root of 2. Square root of 8, because it's cubed. All right, so let's substitute that into my problem. My x cubed is going to become that. My radical is going to become 1 plus u squared. And my dx is going to become this. And put all together, then I'm going to end up with, now the square root of 2 and the square root of 2 here are going to give me a 2. So I'm going to have a 1/4 outside, and then I'm going to have a u cubed times 1, and we'll do it in a fractional power so it matches the formula. 1 plus u squared to the 1/2. All right, so what does that mean in terms of my constants? Basically, it means n is 3, and k in this case is 0, because this is 2k plus 1, and if k is 0, then I get 1/2 as a power. All right, so now I'm going to apply this formula, and it's going to be a reduction formula. So it's not necessarily going to get me all the way to an answer in one step. I may have to apply it more than one time. So For right now, I'm going to get 1 over 2k plus 3. K is 0. So this is going to be 1/3. And then x to the n minus 1 is going to be x squared. And then x squared, or again, not x, it's going to be u plus 1 to the 3/2 minus 2 over 3, 2k, because k is 0, square root of n minus 2, that'll just be x, and then x squared plus 1, again, not x, it's u, to the 3/2 plus c, except that there's a bracket here, and there is a 1/4 out front of this rule. Now, I still have an integral right here left that I need to finish, but this one, I could probably, I don't need to apply this rule anymore. I need to apply a different rule. I need to apply one that's probably already in the table, but that just has a 1 power. So let's go back to the table. So I'm looking for a 3/2 power, maybe, with an x out front. Or I may just do this by substitution, which is probably what I'll have to do. But let's see if we can find, those are linear factors. I need the squared factors. Now this one has the 1/2 power. It doesn't have the 3/2 power. Here's a 3/2 power, but by itself. Not really sure why this formula seems to be in here twice, but oh, it's the difference in sign. Yeah, so I'm not really finding what I'm exactly looking for. So we're just going to go back to our regular rules and finish it by substitution. So let's go back. So basically what we're going to do in this particular scenario is we need to finish out this integral right here. And so in order to do that, there should be a du here. In order to finish that, we're just going to do a regular substitution. I'm going to call it something other than u, since I've already used u for something. And then dw will be 2u dw, and that means that this is going to become and we'll come back to the we'll just substitute it into our formula in a bit. So what we have here is w to the 3/2 and then an extra 1/2 basically for the dw. because we're going to divide this like u du by 2 so that it's just u and not 2u. And so when we do that, we're going to end up with 1/3 something w to the 5/2. And so this will be 2/5. And we already have the plus c up here. So if we go back and we replace w with the u expression again, we're going to end up with 2/15 u squared plus 1 to the 5/2. Now, we want to continue on with the rest of our problem. So what I've done is I've solved for this. So this second expression right here is going to get replaced with this guy. And then, of course, I have to put back my original u, which was this. And so finally, we're going to get back to the x that we started with. U squared is going to become 2x squared. And this u squared is going to become 2x squared. And this u squared is going to become 2x squared. And so, I mean, you can see how we could simplify some constants and things, but basically we've gotten to a point where we have integrated everything. And the tricky part about this one was that the specific formula that we needed to actually complete the entire formula was not in the table. And we had to do a substitution to match the table with something that we could use, which was just a reduction formula. And then the final step we actually had to do ourselves because that specific example didn't actually appear in the table at all. But it was just a u substitution.